Without further ado, Claudia, take it away.
Thank you. Thanks a lot. Thank you so much for the invitation to talk in this series. It's a very exciting series, and thank you for the initiative in setting this up. I think it makes the whole lockdown much easier to go through. I'll start by thanking my collaborators. So if there's anything you may like in this talk today, it's thank you to those collaborators. I'm of course to blame for anything you're gonna dislike throughout the next hour or so. So I'll be talking about the effective field theory of gravity, and the question I like to ask is, within the low energy effective field theory, including gravity, what are the constraints from having a standard Wilsonian UV completion and a normal, a standard one, and what the constraints are from having this low energy effective field theory being causal. So by that I mean enjoying causal UV completion, but also how the notion of causality manifests itself already within the low energy effective field theory. So here's a brief outlook of the field content and symmetry and expansion parameter that I'll be looking at. Throughout this talk, I'll be going back and forth between two types of effective field theories. One which is really for gravity, where I'm integrating out massive particles and I'm considering the effective field theory for gravity. And then another one where gravity could just be an external field, if you were, where I'm more interested in the low energy effective field theory for QED below the mass of the electron. So I'll be a little bit more specific in how when I introduce these effective field theories. But before we introduce the notion of gravity, if I have a standard non-gravitational effective field theory, so it's really just on Minkowski, we do know, and I'll go through that a little bit more, but we do know that if we impose some very natural constraints on the UV completion for it to be causal, local, Lorentz invariant, and unitary. So hopefully we'll all agree that these are quite reasonable assumptions. We may not always want to have those assumptions, but they are quite reasonable. Then we know that the low energy effective field theory should enjoy all the fields being subluminal. So we shouldn't have any speed, any what we would qualify as a speed in the low energy effective field theory ever being superluminal. And related to that point, the scattering amplitude, at least for 2-2 elastic scattering amplitudes computed within the low energy effective field theory, should enjoy some positivity bounds. So I just have one slide explaining that a little bit more in detail. I could give a whole talk on this effect, but let me just give you a brief summary right now. So if we're thinking of the 2-2 elastic scattering amplitude, the notion of causality within the low energy effective field theory, the notion of causality is related to that of analyticity. So I'm not going to go through this relation here, but this is something that has proven extremely well in the 60s. And the notion of analyticity of the amplitude tells us that we can analytically continue it in the complex S plane, and it should be well defined analytic apart from the presence of a few poles and branch cut in the real axis. So in particular, I can perform a Cauchy integration, and I'll just end up with having an integration over the real axis, assuming locality, which manifests itself in a Schwarzschild bound, that the amplitude falls off sufficiently fast as S, the magnitude of S goes to infinity, sufficiently fast as to satisfy the Schwarzschild bound, which tells us that this quantity here is actually going to 0 as S goes to infinity. And it also tells us that this integral there is therefore finite and makes sense in its own right. Then the notion of Lorentz invariance for us is what we're going to use out of that is the notion of crossing symmetry and being able to relate this integral on the positive part of the real axis, S-axis, to that on the negative part of the real axis by crossing symmetry. And then finally, probably the most crucial ingredient in all of that is that of unitarity, which hopefully we all agree we want to impose upon ourselves, which in the sense of the optical theorem tells us that the imaginary part of the amplitude in the physical plane, in the physical region, has to be positive. And the requirement that the imaginary part of the amplitude has to be positive tells us through this Cauchy integration formula or through analytic continuation that the second derivative of the amplitude at as close as we want to S is 0 has to be positive. So those relations directly imply for a non-gravitational effective field theory, when we can apply the notion of analyticity without any subtleties, that this positivity bound has to be satisfied within the low energy effective field theory if the high UV completion satisfies these criteria. And so within the notion of positivity bounds at low energy, or within the notion of requiring the fields to be subluminal, there's intrinsically in all of that the notion of causality. This is really what links the two effects. And for us, the notion of causality in Minkowski is anchored in everything we do. We always tend to assume that if a field becomes superluminal, this will be directly related to a causality violation. What I'll try to convince you with today is that when you're dealing with gravitational theories, so by that when gravity is present either as a dynamical field or as an external field, these requirements of subluminality or the positivity bounds are much more subtle because the notion of causality in the presence of gravity is much more subtle. Just to clarify, the reason why it's more subtle is not because of frame differences in the presence of gravity. That, of course, is a criteria to take into account, but we can deal with that. We can understand what we mean by which frame we're dealing with and what we mean by causality in a particular frame. So these are subtleties, but not really deep subtleties. What we're going to be talking about more is the fact that in a gravitational theory, if we're not in Minkowski per se, the notion of an analyticity, which is related to that of causality, is much more subtle. And we see directly how the positivity bounds can manifest themselves slightly differently in gravitational effective field theories. And that is directly linked to some subtleties related to what we mean by sub or superluminalities in low energy effective field theories. So it's actually simpler to start with the positivity bounds and understand why those bounds are more subtle in gravitational effective field theories. And this is just because of the possibility of having an exchange of massless spin to field. So even if you don't care at all about gravity, you just do, I don't know what, what it is interested in. If you do scattering of electrons or the Higgs field, or if you're interested just of scattering of the inflaton, no matter what you're interested in, even if gravity is really not at all something you care about, because whatever theory you have will ultimately be embedded within a gravitational theory, you cannot prevent from having some interaction with the graviton and whatever two scattering amplitude you're considering, you cannot prevent ultimately to having an exchange, a graviton exchange, which will manifest itself through the presence of a T-channel pole in your scattering amplitude, even if the amplitude you're considering is that for a completely different field, which is well defined and couldn't care less about gravity per se. The issue with the gravitational exchange is that this amplitude, or this T-channel pole amplitude, grows like S squared, and therefore we can't subtract this pole from the amplitude because this saturates the Froissart bound. And so if we subtracted it, we would have no reason to believe that the remainder would itself satisfy the Froissart bound. And this pole by itself violates, well, it's a singularity, so you couldn't have analyticity requirement for per se. So the presence of such a T-channel pole in a gravitational theory, even if you don't care about gravity, compromises the direct application of the positivity bounds. And this, again, is very different than if you're just considering the exchange of a massless spin-1 field, for instance, for the photon, for instance, because it will just grow in that case like S, and then you could remove it, it wouldn't be saturating the Froissart bound. And also, if you wanted to, considering an exchange of a massive spin-2 field, then you would have a mass coming into the denominator here. And so this would be a safe thing to do. You could evaluate it at t is equal to 0 without any issue. So if you want to deal with this issue by going to massive gravity, you're welcome to do so. But it is an issue as soon as you're dealing with a massless spin-2 field or a massless higher spin field. As we know, this is always related to some subtleties. So This, of course, is a well-known issue, and it has promoted the development of many ways to be dealing with it. And recently, there's been a very interesting way that has been put forward. And if we could use it, then it will radically change our perspective in the positivity bounds in gravitational low-energy effective field theories. And the very clever aspect of what was put forward is to realize that this is really an issue in 4 dimensions where the graviton is dynamical. But if you're dealing with 3 dimensions, if you're thinking of a 3-dimensional space-time, then the graviton would not be dynamical. And therefore, there shouldn't be a T-channel pole associated to the graviton because it's not dynamical. So if you can use that fact to thinking of taking your 4-dimensional space-time, compactifying one of the dimension on a circle, it can be a very large circle, and then if you just focus on the 0 mode corresponding to what would otherwise have been the massless mode in 4D, as the 0 mode in 3D is not dynamical, and therefore we shouldn't get a T-channel pole associated with it in the amplitude in 3 dimensions or in this compactified space-time. So you can in principle first compute the amplitude in this compactified space-time, but at the end of the day, nothing prevents you from sending the size of this compactification to infinity and recover back 4 dimensions. So with this approach in mind, what it seems to suggest is that a priori, we should be able to apply the positivity bounds to the T-channel subtracted amplitude, because the T-channel pole should not contribute in 3D, but then the positivity bound should be valid in 3D and you can promote it back in 4D at the end of the day. I'm not making justice to the beauty of this argument. If you want to see any of the details, you can look at this. There's been a few potential caveats that have been pointed out in the literature since then. So what I'll be doing for the next few slides is to explore the validity of this argumentation and more the validity of this T-channel pole subtracted positivity bounds in a particular example where we do know an explicit partial UV completion, and therefore we can compare what we have from the partial UV completion and from the positivity bound applied on the T-pole subtracted amplitude. The example I have in mind is that of QED coupled to gravity. Because I'm very lazy and, and I don't want to do everything right now, I'll just consider a scalar version of QED. The fact that it's a scalar version of QED is mainly me to blame for my laziness. It doesn't really impact very much on the final results. It's just a little bit more complicated, but not much more. So I'm considering actually a scalar photon. My A here is a scalar, and a scalar fermion, a scalar electron. So my psi here is the scalar analog of the electron. So this would be my QED, and I have this coupling between my photon and my electron. Now, this is embedded within a gravitational theory. So I have gravity in here, and I'll consider, just to simplify my life, I'll consider a spectator field. Chi is a spectator field, which in the absence of gravity would just be living its own life, not coupling to anyone in the world, but because we include in gravity, this spectator field indirectly through gravity couples to the photon. And so I can compute some 2-2 scattering amplitude, so an elastic one between the photon, my scalar photon, and my spectator field. This field can be really whatever you want, anything in nature. I can compute this elastic amplitude, and I will have a contribution coming from the gravitational exchange. Of course, when I send M Planck to infinity, if I decouple gravity, then the spectator field and the photon do not interact, but they do interact as soon as M Planck is finite. So this would be just what we would have in the absence of the electron. But now what we're really interested in is loops of the electron. So if we're looking at what the effect of the electron on this 2-2 scattering amplitude. So in doing so, we can compute the result. It's not particularly interesting to go through the details. And as promised, we will have a T-channel pole, which is directly related to this gravitational exchange in here. And then from here, there's no T-channel pole, but we have the contribution from the mass of the mass of the electron, which is present in here. So in that particular example, of course, as soon as you include gravity, this is not a UV complete theory because gravity is not renormalizable, but hopefully we can agree that it's a partial UV completion. Okay, so the presence of the non-renormalizable operators is simply due to gravity and to nobody else. Now, if I were to take this amplitude and apply the T-channel pole as suggested from the compactification to 3D, so if I were simply able to remove this T-channel pole following the argument that if I were in 3D, this would not be dynamical and so it shouldn't be there, what I would end up with is simply the requirement that the remainder here has to be positive. But in this explicit calculation, we just do it brute force, where we see it is actually negative for anything that satisfies unitarity. If the coefficient alpha here are real, if nothing goes wrong, we will end up with something which is manifestly negative, even though the T-pole subtracted amplitude tells us that it has to be positive. And again, I've done this for a scalar example. It's mainly due to simplification. You can do it for real QED, minimally coupled to gravity, and you would get very similar type of results. So at this stage, we really have two possible conclusions. What we see is a contradiction between the bands, which would have expected to be satisfied, and an example, which is a scalar version of QED, or QED, minimally coupled to gravity. It should be gravity here, sorry, not QED. So from there, you can conclude two things. Either it's simply not consistent to take this scalar version of QED or QED being minimally coupled to gravity, without also including other operators which have to come in below the Planck scale. So it has to come in at a scale which still goes to infinity when the Planck scale goes to infinity. Because the issue is all related to the coupling with gravity, but it's actually parametrically smaller than the Planck scale, and it's weighted by the mass of the particle that we're interested in, which is the mass of the electron. So that would mean that for these bands to be satisfied, you would need to have new operators between your photon and whatever other massive spectator field that exists in nature, no matter what its mass is, so long as it's below the electron mass. You always need to have additional operators at a scale which is given by that, which is roughly 10 to the 16 electron volts, so 10 to the 4 TeV. So, I mean, this result would be amazing. If correct, this really, we should just sit down and write down a proposal for the next, for the next particle accelerator, because we would see so many new interactions going on at 10 to the 4 TeV between the photon and every other particle that exists in nature, even if we didn't think it should couple to the photon directly prior that. So that's a really amazing result in itself, but it relies on the assumption that those bounds are valid. So before we jump into this conclusion, we should just ask ourselves whether another possibility is that those 3D compactified bounds are maybe not as justified as we could have otherwise assumed. And there are reasons to believe they may not be entirely justified, or some potential caveats that have been pointed out in the literature, and some of them I'll summarize in here. So a lot of those are related to some subtleties with the amplitudes in 3 dimensions. So while it's true that gravity is not dynamical in 3D, it's not quite true that the T-channel pole completely disappears when you're performing the amplitude perturbatively in 3D. What does happen is that when you compute the T-channel pole, when you compute the amplitude in 3D, you do see a T-channel pole, but you can argue that it will disappear after you resum, you perform an iconal resummation, it will factorize out as a delta function. But the presence of this delta function is really in itself a singularity, or in other words, is the 3D manifestation of the pole we had in 4D. It's in by itself a violation of an analyticity. And you can try to define an amplitude where you have removed this delta function from the outset. This has been tried in the 90s, but then that comes at the cost of violating the positivity of the resulting amplitude, because the positivity of the amplitude is only manifest in the presence of this delta function. But in the presence of this delta function, you can't just apply the positivity bounds because you require the analyticity argument. There's been other ways put forward, attempts to be put forward in resolving this issue. One interesting one is to computing the amplitude by first redressing the gravity states at infinity. So thinking that whatever particle you have there is going to create a conical deficit angle. You can define your asymptotic states redressed from this geometry and then compute the amplitude. But you have to be extremely careful in doing so that the resulting amplitude does satisfy the crossing symmetry. And there's to date no explicit formulation of the 3D amplitude which satisfies simultaneously all the criteria that are required to prove the positivity bounds. So at this stage, it's really up to you to decide whether you think that the blame is to be put on QED minimally coupled to gravity, or whether we need to justify the 3D compactified bounds a little bit further. You can take whichever approach, and I think both of them are very interesting. But for the rest of my talk, I'm going to assume that possibly the 3D compactified bounds are not justified, and therefore we can't simply apply the positivity bounds on the T-channel subtracted amplitude. And so with that in mind, a priori, the best thing we can do right now is simply to argue that the positivity bounds have to be satisfied if gravity was not there. So in a limit where you send the Planck scale to infinity, and that requires starting in a frame where you can decouple gravity entirely. So you first need to put yourself in that frame, and this is related to the comments I made earlier, where, of course, in the presence of gravity, there's some frame artifact one can get confused with. But right now, I'm going to put all of that aside. I'm going to start with a frame where I can decouple gravity altogether. And in the limit where M Planck goes to infinity, then there's no issue with the T-channel pole, and I should be able to apply my standard positivity bounds to the mean of the amplitude. So more precisely, if you go through the details, what it means, and we'll see that when we look at the causality arguments later, is that if you do have a 2-2 scattering amplitude, which does have a T-channel pole of this form suppressed by the Planck scale, then the remainder itself here, the coefficient C here, does not need positive, but rather has to be larger than that quantity, which would simply be 0 when the Planck scale goes to infinity. But when the Planck scale is finite, there still is the possibility of having a small negative quantity suppressed by the Planck scale, as is the case in the partial or the QED example we looked at, minimally coupled to gravity. Okay, so to understand how this is related to causality, I'm gonna change slightly effective field theory for a little bit before I go back to the example of QED. There's a lot we can say about causality and the relation of those bounds when we're dealing simply with the low energy effective field theory for gravity. And when we understand how to deal with that in this low energy effective field theory, it'll be much simpler to apply the same type of arguments in the context of QED. So for the next 15 minutes or so, what I'll be looking at is the effective field theory for gravity. What I mean by that is I have a high energy theory, which may be complete, which has gravity or whatever you want in nature. It has some light and some heavy modes, and I'm integrating out all the heavy modes below the scale, above the scale m, to end up with a low energy effective field theory for gravity that has a cutoff, which is m or lower. So this is just being a little bit more explicit. A priori, we have all the fields in nature here, and we're just interested in the low energy effective field theory at here. So there's a few terms in this low energy effective field theory I'm gonna go through. There is the standard cosmological constant. I don't know how to deal with it. So I'm just gonna ignore it and move on. So this is not a concern in here. There's the standard Einstein-Hilbert term, which we're going to keep. They are the coupling to all the light matter fields, And I will assume this matter field to be minimally coupled to gravity. Actually, that's not quite true. What all I need is to ensure that there's at least one light field which is minimally coupled to gravity, so that I have a notion of what I mean by having a standard speed of light in the vacuum. Okay, I just want one field to not to have some subtleties related to its coupling to gravity. So I just want to have a reference. This is not very important in itself. Then we have all the curvature corrections to that. In particular, we have these R-square corrections. And it's quite standard when dealing with the effective field theory, particularly when you're dealing it on Schwarzschild, or I'll be dealing it on FRW in here, to remove these R-square operators via field redefinitions. When you do so, you include non-minimal couplings between your light fields and the curvature terms, and that changes what I mean by my notion of causality slightly. It changes slightly what I mean by my notion of luminality. And so in order to avoid any of those things, I'm gonna remain in a frame where I keep this R-square correction in here, and I'll keep my matter field being minimally coupled to gravity. So with that in mind, this is my low energy effective field theory. I can include my curvature cube operators and everything I want in here. Just to be clear, I've been asked to specify the field content, the symmetries, and expansion parameter. So I have in my low energy effective field theory, I have the graviton, I will have light, and any other massless or light particle minimally coupled to gravity in here. The cutoff is the mass of the lightest field you have integrated out. So we'll have a cutoff M. It's fully covariant, and we have all the symmetries for the matter field that you need to have, the relevant context. And so far, the expansion parameter is the curvature of the cutoff square. I will go a little bit more by what I mean, not so much about the expansion parameter, but more what I mean in being within the regime of validity of my low energy effective field theory in a second. So now I'll use this low energy effective field theory for gravity, and I'm gonna put it, just because I can, just because it's simpler for me, in the cosmological setup. I'm gonna consider tensor fluctuation on FRW. So the fact that we have some non-trivial geometry will mean that we'll have some non-trivial propagation of the field, and in particular of gravitational waves. When I'm on FRW, the propagation for the gravitational waves, including those operators from my EFT, will lead to a small departure of what we call the speed of propagation of the gravitational waves. And we can see that the speed of propagation, or what is qualified as the speed of propagation of gravitational waves in any effective field theory of this sort, in everything that is done in cosmology. So I'm using the same definition as everybody else, just as much to blame as everybody else. That's a pretty poor excuse, I know. This notion of speed of sound or speed of the gravitational waves is given by 1 in the absence of the EFT operators, but as soon as we have those operators, we'll have a small departure from luminality, from exact luminality of gravitational waves. And this is true so long as I am within the regime of validity of the effective field theory. So we'll have some curvature of a Planck corrections operators, and then we'll also have some corrections that come from the fact that if I'm a high wavelength for my modes, then I'll need to take into account other things. So that at high energy, the speed of gravitational waves will go back to being exactly luminal. So one thing we can check is that if we were dealing with a maximally symmetric space-time, if h dot was 0, so if we were in exactly de Sitter, this departure from luminality would vanish, and that is as it should be. The fact that gravitational waves are traveling at a speed that isn't exactly what we would qualify as luminal speed is really because of a spontaneous breaking of Lorentz invariance, and here it's a spontaneous breaking of the maximal symmetry of the space-time, and it should really be carried by this breaking of the full maximal symmetry. Okay. Another point, just to be very clear, the order of magnitude of this coefficient should be maybe a 4 to 1, unless I start abusing my effective field theory, but let me not do that right now. So this should be a 4 to 1, which means that the order of magnitude of those corrections are ridiculously small. This is not something I'm expecting to measure in the next 1,000 years. It's not about whether the speed of gravitational waves measured by LIGO is consistent with this effective field theory. It's not about that. It's about whether gravitational waves are allowed or not to be what we would qualify otherwise as being superluminal, or whether we should actually segregate between different types of effective field theory and set up a prior on what the sign of those coefficients should be. Okay, so if H dot is non-zero, so if I have a spontaneous breaking of my maximal symmetric spacetime, and if the non-energy condition is satisfied, then H dot is negative, which means that imposing subliminal, what we would qualify as subliminal speed at low energy for gravitational waves, would require to impose this coefficient here to be negative. And this is typically what is done in almost all of the effective field theory for cosmology literature that is done. And a lot of the time when comparing with data, there's a prior that is being made on the sign of operator so as to ensure that the speed of every field, including the graviton or including gravitational waves, be subliminal. So the question I'm going to ask is, in here, should we really impose on ourselves that this low energy effective field theory for gravity that I just obtained from integrating out various fields, and if I integrate out various fields, sometimes this coefficient C will be positive, sometimes it'll be negative. It depends a little bit on the context. So should we really segregate between this type of effective field theories, or is it possible that this coefficient here could be positive? And when I go back to what the connection we had with the causality in the UV completion and the positivity bounds, what this required us at the time, when I did that before, is having our effective field theory satisfying the positivity bounds, the standard positivity bounds in the limit where gravity decouples, which told us that this coefficient here should mainly probably be positive. It can be a little bit negative, but not by a large amount, or by an amount which is suppressed by the Planck scale. So if we were to impose both criteria, really, that wouldn't leave much room for this coefficient at all. I mean, that by itself would be a huge statement. So what I'll try to understand in what follows is whether we should really satisfy that bound, or whether it's possible simply to have C omega squared being larger than this small negative amount and still be consistent with causality within the low energy effective field theory. And this I'll emphasize, I'm really asking the question within the low energy effective field theory. There's no question that when going to high frequency, the speed itself, we return to luminality, to what we qualify as exact luminality. And so the front velocity itself will be luminal. So the UV completion has no issue with causality per se, but within the low energy effective field theory, there's still a requirement of understanding how what we would qualify as superluminal velocity is consistent with causality. Because if we just put ourselves in the low energy effective field theory, a priori, we can integrate out, or can wait in this cosmological setup as long an amount of time as we want, so that there's as large a propagation outside the standard light cone as we want. So we could start with a configuration, let's say, where we know we will have no violation of where we're in Minkowski, let's say, or where we're really in a maximally symmetric space-time, where the gravitational waves travel at the speed of light, as it should be. And then I have a blob of matter or cosmology or whatever I want in between. I use this to have a propagation outside the light cone, which is extremely small, but still I can integrate it out for an infinite period of time and then go back to something where I can compare between the normal propagation and my propagation of gravitational waves, and I have as large a support outside my light cone as I would want to within my low energy effective field theory. So it is this specific question I like to address within the low energy effective field theory. and not so much how much this low energy effective field theory recovers causal structure at high energy. So when we think of this low energy effective field theory, everything really has to be boiled down to whether or not we're remaining within the regime of validity of its effective field theory. We know that it has a cutoff because we integrated out some fields of mass m, and so this effective field theory has a cutoff m, which is below the Planck scale. I'm going to take it to be the Planck scale to be quite conservative, but really the cutoff should be below the Planck scale. So that means that in order for the computation to be within the regime of validity of the effective field theory, if I have any mode with physical frequency k, it will lead to some operators, which are what we would have had in Minkowski, plus some correction related to the fact that I'm on FRW. And those corrections have to be smaller than the cutoff square, or smaller at the very least to the Planck squared. So if I implement that into asking for how big an amount outside my light cone I can propagate using this type of cosmology, or this type of support, you can think of an experiment where you send in a wave with given physical frequency k or wavelength lambda. And if you send it early enough time so that that's where you have the most deviation from luminal speed, that's where you generate as much as possible as support outside the light cone. You can ask the question, how early can you send in your wave so that you still remain within the regime of validity of the effective field theory? And so for a particular mode or for a particular wavelength, there's actually a bound on how early you could have sent off that mode. So for a finite lambda I, there's a maximal Hubble parameter at the initial time where you send in the wave that you need to satisfy to ensure that you're remaining within the regime of validity of the effective field theory. And that directly translates into a bound on the amount of support outside the light cone that you can generate using this type of setup. So when you compute the physical distance outside the light cone you could have generated by integrating from an initial time I to infinity, it doesn't matter too much until when you do, you stop the experiment because you're assuming that you're preserving the next, so h is decreasing. What you end up with is this distance being always much smaller than the physical wavelength of the mode that you have sent in. So even though you do seem to have a support outside the light cone within the low energy effective field theory, this is always by an amount which is smaller than the wavelength of the mode. And so everything, there's no optical approximation here. You're not in the resolvable limit of your theory. You can't resolve that amount of support outside the light cone. And so from those considerations, you cannot conclude that there is any violation of causality. So this is easier to understand within the cosmological setup, and particularly that in the cosmological setup, you could have thought in principle that you could have integrated for an infinite amount of time, and you would have had an infinite amount of support outside the light cone. But what we see is that in order to remain within the regime of validity of our low energy effective field theory, there's actually a bound of how much support outside the light cone we can obtain from such considerations. So within this philosophy in mind, I'm going to go back to the effective field theory for QED below the mass of the electron. And then I'm going to see how we notice this small violation of what would have been otherwise the positivity bounds in the absence of the T-channel pole, and how this is connected with the fact that this is a well-known fact that in QED, in the low energy effective field theory for QED, on curved space-time, we can observe what would qualify as a superluminal speed for the photons themselves. So this has been very well studied since the 80s, and there's been a whole series of very interesting literature since then. So the effective field theory I'm dealing with here is that of the photon below the electron mass in the presence of gravity. So we have gravity manifesting itself through curvature corrections here. For this particular setup, we don't really need to have gravity being dynamical to see the presence of superluminalities, but of course, we need it to be dynamical to see the T-terminal pole in the amplitude. So what has been observed for now 40 years or so is that in this low energy effective field theory, as the photon propagates, you can think of it as interacting with virtual pair of electrons, and so it sees its neighborhood like that, or it sees the curvature of its region. And its non-minimal coupling with the curvature means that you can have an effective speed for the photon at low energy, which could be superluminal. So this has been observed by observed, I mean, mathematically seen about various backgrounds, for instance, Schwarzschild or various conformally flat backgrounds. So the simplest configuration we can think of right here is for black hole configurations, where it's been shown that the speed of light, now I'm dealing with the speed of light on this background, needs not be superluminal. Needs not be luminal. Actually, it has corrections, and those corrections are weighted by a factor which depends on the polarization of the wave. And there's always a polarization for which this becomes positive. In the case of Schwarzschild, it's for radially polarized light. This contribution here is positive, leading to what we would have otherwise qualified as a superluminal speed for light on Schwarzschild due to its non-minimal interaction with the curvature at energy scale below the electron mass. So, and this low energy superluminality and the amount of superluminality we have here is precisely related to the non-positivity bounds, or the amount by which the positivity bounds were not positive, that we discussed earlier. So again, in this particular case, there's no question that as we go back to high energy, when I go to sufficiently high energy, I should go back to reintroducing the electron in my field theory. Those corrections are not there. And there's no doubt that the photon will just be dictated by the standard operator here, and it will recover exact luminality. So the speed does return exactly to exact luminality at high energy. However, the question again is not so much about how this connects back to exact luminality at high energy, is more how to make sense of the low energy effective field theory within the causal context at low energy. So if you think now in a Schwarzschild or black hole configuration, I can imagine that I'm sending two signals, one of light and one of another massless particle, whatever it is, which doesn't have this non-minimal coupling with gravity. So this would be the null geodesic, then all the well-behaved particles will follow. However, the geodesic followed by light in this low energy effective field theory for QED will follow a slightly different geodesic, which can result into a time advanced when we're comparing it after the scattering. And again, a priori would have at every point a very small amount of superluminality, but in principle, we can integrate along the whole configuration, or we can superpose as many black holes as we want, so as to increase as much as possible the support outside the light cone, or to make this time advance being as large as we want. So this is really the issue here. So what was previously argued is that in principle, it would be okay for this quantity here to be negative, corresponding to a time advanced, as opposed to a time delay. It could be possible for this quantity to be negative so long as the whole contribution itself is sufficiently positive. So there's various contribution coming to the time advance. There's the one coming from the fact that you are on a curved geometry, and so you have a time advance compared to what you would have had otherwise on Minkowski. And then in addition, light in this low energy effective field theory acquires an additional time advance or time delay coming from its non-minimal coupling with the curvature. But asking for the whole quantity itself to be positive and allowing for this quantity to be negative by itself is not enough, because if you allow yourself to have this small, this contribution to be negative, then you can think of configurations where you can abuse the system and you can really have a support outside what you would have thought are your null geodesic, or outside the light cone set up by the null geodesic of your system. And as soon as you do that, typically this is related to a violation of causality. But now we've seen in the previous cosmological context how we could deal with this type of superluminalities and how they could be consistent. And the resolution here has to be very similar. So I'm just going to focus on the extreme case scenario where actually the deviation from luminality is maximal, very close to the impact parameter. At that level, if you can take it to be very close to the Schwarzschild radius, as close as possible as you can. You can't quite go to the Schwarzschild radius itself, but you do it as close as possible as you can. Then, unsurprisingly, the deviation from the speed of light is just carried by the cutoff of EFT and the curvature scale of the black hole. And so that leads to a negative time delay. In other words, a time advance. So light would come in before what you would have expected as set up from your null geodesic by an amount which is precisely set by the curvature of or the mass of the black hole and the cutoff of your EFT. Now, again, the fact that you need to be within the regime of validity of your EFT is key in understanding how relevant this negative contribution is for all intents and purposes. So within the low energy effective field theory, we know that it's only valid if your operators are below the cutoff of your EFT, so the mass of the electron, for instance, in this case, which means, again, that all the curvature corrections have to be small compared to that mass, but also any scalar invariant that you construct out of the wavelength of the mode that you send in with the curvature itself has to be smaller than the cutoff. And this is really what is relevant in this context. And this is similar to what we discussed about in the case of the cosmology, where this was more symbolic in the case of cosmology, where we're looking at the correction to the Minkowski operator. Here, hopefully this becomes a little bit clearer. So in the extreme scenario, where we're just looking at a wave at the impact parameter, so it's purely transverse at the impact parameter, you can ask for this quantity to be satisfied there. I'll take it to be as close as possible to the Schwarzschild radius. So that's why all I have is the Schwarzschild radius. This is going to constrain the asymptotic energy of the particle that you can scatter. So if you want to send in a particle and if you want to send in a wave and ask it to be as close as possible to the black hole so as to extremize the amount of superluminality that you're going to enjoy, there's going to be a bound on how large the energy of the wave you can send in is. And so turning it around, it tells you that you need to send in a wave with sufficiently large wavelength in order to enjoy this level of superluminality. And that, again, you're going to see that this implies in return that there's a tension between how much how small a wavelength you can send in, and how large a support outside the light cone or how large a time advance you can build in for yourself. The two are directly in tension with one another. If you want to compute, if you want to get a large, let me just compare those two. The time advance has to always to be smaller than the wavelength of the mode that you sent in. And so again, we see that in this context, even though there seems to be a time advance in this configuration, it's never resolvable. It's always unresolvable, as it should be exactly in the same way as it was in the cosmological setup for the EFT of gravity. So in other words, if you try to make advantage of the curvature of your space-time by getting as close as possible to your black hole, you're going to need to decrease the asymptotic energy of the wave you sent in, or increase the wavelength of the wave you sent in. And in doing so, it means that you're always going to end up with a time advance which is smaller than the wavelength of the mode that you sent in. So, and we can see that in this particular case of QED, it's precisely where it saturates. It's the last time it saturates the bound. We don't have so many powers of M Planck to play with in here. And these are details that I can discuss much more in detail later on, but you can see that in this type of effective field theories, you can allow yourself for what you would otherwise qualify as a level of superluminality, so long as, of course, it goes to zero when the Planck scale goes to infinity, because it's all due to gravity, it's all gravity to be blamed, but it has to do so fast enough. So the level of superluminality you can allow for yourself while remaining consistent with causality has to scale like the Planck scale with at least 2 powers or faster than that. And this is directly related to the level of positivity violation, if you were, then you could allow for yourself in the positivity bounds in the presence of the T-channel pole. So those two scaling are precisely the same. So I think I'm burning slightly out of time. Let me just make a few quick comments before I conclude. One thing that I'd like to emphasize is that it may seem that the conclusion of what I'm trying to say is quite trivial, and it is, of course it is completely trivial, but maybe not for quite the same reason that as everybody thinks. What I'm saying is not that in order to remain within the regime of validity of the effective field theory, the amount of support outside the light cone will, what I'm saying is not that the amount of support outside the light cone will always be smaller than the cutoff. I am not saying this statement. And if that was the statement I was saying, then it would still be an issue with the whole philosophy, because I'm only using the low energy effective field theory to computing the trajectory, or to computing the geodesic of the wave. But not once I've computed it, nothing prevents me from using a new apparatus at very high, that requires very high energy or very high wavelength, so as to measure a very small distance of a very small support outside the light cone. So it's not sufficient to asking that the support outside the light cone is smaller than the cutoff. This is not really the relevant quantity. What I'm saying is that the support outside the light cone is not within the resolvable limit of the wave I have sent in. And so we're using some type of optical approximation when sending in the wave and following a geodesic. If I'm looking at corrections which are themselves smaller than the wavelength of the mode I'm sent in, then I need to take those corrections into account in order to be saying anything particularly related to causality violation. So that's one point. And a second point of what I'm trying to say is, a priori, it seems that if we have an amount of time advance, of time delay, which is smaller than the wavelength of the mode that we sent in, I'm concluding that we cannot directly link this with causality, because we need to account for other effects related to the wavelength of the particle. But actually what I'm trying to conclude is something slightly stronger than that, which is not only that there's no direct link with violation of causality, it's more that if what we observe is a time delay which is smaller than the wavelength of the mode, then really we can conclude that causality is preserved. Because if the time advance or the time delay is sufficiently small, then nothing prevents us from computing the retarded computing the green function in the EFT perturbatively about what it would have been in the absence of the EFT operators. And then by definition, what I will end up is simply exactly the same light cone structure. So this is, again, going back into the cosmological setup. Sorry for going back and forth with that. But typically, if I have some speed which is different than one of these four, the reason we don't allow ourselves always to compute the propagator perturbatively, and why we are worried with non-luminal speed, is because there's a potential presence of growth of the secular effects. And this is precisely related to the fact that the question I was asking, how big a support outside the light cone can we accumulate? If those effects start becoming large, then this perturbative approach breaks down, and there's no reason to believe that the propagator we would compute in the EFT could have a support which is different from that we would have computed in the absence of the EFT operators. But so long as this quantity is small, then, as I mentioned, we ensure that those secular effects never become large, and so the perturbative analysis is always an appropriate one. And in performing appropriate expansion, we can never have anything other than precisely the same light-cone structure as we would have had in the absence of the EFT operators. So I'm trying to say that in a different way, but if this secular effect never become large, because this is always small, then I can always compute my propagator in my EFT perturbatively about the retarded propagator, and all I'm gonna end up having is operators acting on my delta function, or my theta function, sorry, from my standard retarded propagator, but acting any operator on it that I want will not change the fact that it is remaining zero outside the light cone. And so I'm ensuring that the propagator for my EFT satisfies the same light cone structure as the one I started with originally, in absence of the EFT operators. Okay, and for those of you who are interested, some of those calculations are often done in terms of the phase shift. Here I've been doing it in terms of the time delay or time advance. None of that is particularly relevant. You can really jump from one to another at wish. Okay, so I'll end up here. I think I'm running a bit out of time. So let me just emphasize again, with respect to comparing with observation, there's no reason, there's no question that the speed of gravitational waves and the speed of light is extremely close to luminal. What I'm trying to address is not really something directly in comparison with current observations. It's more in trying to understand how the notion of causality manifests itself in low energy effective theories that include gravity, and whether we should and we are allowed to segregate between different types of effective field theories based on the operators that lead to speed of either being superluminal or being subluminal. There's a question of frame that I'm not going to address here, which is very well under control. This is all very well understood, so let me not talk about that in here. But so long as you're working in a frame where you can decouple gravity altogether, you can still, in that frame, be led with gravitational waves or other fields that have a tiny amount of what you would otherwise have qualified as superluminal, but this is not in conflict with causality. And it may even be consistent with causality, or sometimes causality imposes you to have the sign for gravitational waves to be exactly what you would have qualified as being superluminal. And this is consistent with causality so long as the amount of deviation from luminality is sufficiently suppressed by the Planck scale. And there's a direct connection between that and between the fact that we're observing a presence of a T-channel pole in scattering amplitudes, which prevents you from directly applying the standard positivity bounds in the presence of a gravitational exchange. But instead, the best thing you can do is asking for those coupling constants not to be strictly positive, but being slightly negative by an amount which is still suppressed by the Planck scale. So I'll stop here, and sorry for running